Let's have a look at a polynomial regression. I'm going to work through, I haven't given you a copy of this and there are no to-dos. I'm just going to try to illustrate to you polynomial regression and overfitting. Here goes. We're just going to get some libraries, create some data. I will do this slowly just so you get an idea of how to do this, because we might set a homework similar to this later on. So the first thing we'll do is we'll set a random seed, and we are going to simulate 3030 different observations. Our independent variable x is just going to be sampled uniformly from the interval 0 to 1. If we look at what we get when we do that, it's not very exciting. It's just an array of 3030 numbers that lie between 0 and 1. The basic pattern that we're going to say that the target variable follows is the sine of 5 times x. But we're going to add a little bit of noise to this random variable, just like you would have in real life. You're never really going to get data where the y values are not noisy. Noise will come from a normal distribution, mean 0, variance 1/3, and again there's 3030 of those, and we're going to add the noise to y. We will store all of this in a data set, which only has 2 columns, one for y and one for our first x. I'm calling it x1 because we're soon going to create x underscore 2, which will refer to x squared, x underscore 3, and so on. Finally, we're going to create train data on which to train the model and test data on which to test the model. I'm not going to give the train data very many observations, just 30. But there will be plenty of data on which we test the model, the other 3000 observations. Incidentally, in setting up this experiment, in order to illustrate the point, we're only using a little bit of data for train. There's actually something interesting going on here. It's hard to create experiments which show lots of overfitting when you have huge amounts of data. And this should suggest a strategy for real life. If you're trying to create really accurate models which don't have overfitting, one of the best things you can do is gather more data. Let's plot the data. The whole data set looks like that. Sine of y is sine of 5x, and if we just plot the training data, there you go. It is noisy because we added noise to it, but you can see the underlying relationship just about. And the question is, can we use polynomial regression to try and recover the underlying relationship? Well, let's find out. What this little bit of code does is to create an extra 15 columns, x squared, x cubed, x to the power of 4, and so on. With these features which we're engineering, polynomial features, we will be able to do polynomial regression. There you go, that's an idea of what the data looks like. So here we have the original x, and you can see over there 0.77854 is simply that value squared, and so on. X cubed, x to the power of 4. If you have enough terms in your polynomial, you can fit pretty much any shape. But the question is the shape you end up with any good at predicting data we haven't yet seen? What's going on here? Well, you should be a little bit familiar with this by now, hopefully. It's a linear regression class. And what we're going to do, we pass it some data, we pass it the degree of polynomial that we want to fit, a 5th degree polynomial, whatever it is. And what basically goes on over here is we set up some data to use, and we simply fit a linear regression, but using the polynomial data. Now, actually, there's something I think I need to mention. So I'm going to stop this for a second, and I'm going to mention it, and then we're going to come back. The question is, I've written out a model here. Y equals beta naught plus beta 1x plus beta 2 x squared, and so forth. Is this a linear model? What do you think? Is it a linear model? I mean, it has all these x squareds, x cubeds in it. Is that linear? And the answer is yes, it's a linear model. Sorry, just cracking myself up with my rubbish writing. It's, by the way, very hot outside today, and I can't bear hot weather. so I'm busy melting as I'm recording this. Now, back to this. Why is this a linear model? Because y depends on the coefficients in a linear way. The coefficients enter the model in a linear way. If you had a model which looked something like this, that would not be a linear model. Why does all this matter? Because if you remember, when we had lot area and we had sale price, the relationship between sale price and lot area was something like this, if you remember. And you might have despaired. Can we use a linear model to fit this? Well, now that you know that a linear model does not mean that we have to have something like that, because we can have lot area, and then we can have lot area squared in our model and lot area cubed in our model. We can have all these things in our model, we can create these features, and it will still be a linear model because the coefficients beta 1, beta 2 and beta 3 enter in a linear way, and so long as we have enough of these, we're going to be able to fit whatever shape we need to fit. That's what I wanted to say about linear models. Let's get back to the Python workbook. By the way, if you can hear that humming, that massive humming in the background, it's my machine sounding like it's going to blow itself up. I think it does that every time I try recording myself. I will try to use some editing to get rid of this background noise. But anyway, here's a function which fits a polynomial regression, which is still, as we just said, in the family of linear regression. Let's fit 2-degree polynomial to our data and have a look at the parameters. Here we go. Not massively neat, but you can see there's the model that was fitted. So minus 2.59 times x squared plus 0.5 plus 0.77. Notice that the coefficients aren't very big. Now let's have a look. At what that model actually looks like. Incidentally, I guess we should have started with a 1-degree fit. Let's do that quickly. A 1-degree fit, as you should understand, is going to be a straight line. Now that in no way captures the underlying pattern that you can see in the data. What did 2 do? You can see it's already begun to capture something, but if we look at it how it performs on the test data, again you can see it's missing something. It doesn't go down at the beginning, it doesn't go up in the middle. How about a 4-degree polynomial? Well, that's actually done not too badly on the training data, and even on the test data, well, at least within the range of data that we've given to it, it hasn't done too badly over most of the range. Finally, let's have a look at the coefficients in the polynomial. In order to get the 4-degree polynomial to fit reasonably well, you can see those coefficients are starting to be slightly large, and they all go in opposite directions. This should begin to remind you of some of those wacky coefficients we had in our linear regression model in Amy's house pricing last week. Finally, if something looks good, why don't we just go to the extremes? Let's use a 15-degree polynomial. Well, firstly, look at that. It's just all over the place. It has gone to incredible lengths to squiggle itself. That's not an official technical term in machine learning, by the way. To try and get to every single dot, every single observation. And look at these coefficients. 3.756 times 10 to the 8. They're massive. And again, they're all going in opposite directions. That's a plus, that's a minus, that's a plus, that's a minus, and so on. What did we learn from all of that? Well, we learned a few things. Number one, as an aside, we learned what a linear model really means. We also learned what polynomial regression is, and that polynomial regression is still a linear model. But more importantly, we learned that as you try and make a model more and more complicated to try and capture the complexity of real life, if you don't have enough data, your model can actually overfit itself to the noise in your data. This overfitting is not a good idea, and we need to deal with it.